All right, this is our introduction to the lesson on orbitals and electron configurations, and I'm going to try to go kind of quickly through this. If it's too fast, you can always pause, stop, back up, replay. So our overall goal, we're going to update our model for how electrons are arranged in atoms, and we're going to practice representing them three different ways. So our learning targets, we have a lot. We're going to talk about each one as we get to it, and they're written in the lesson. What we know about electrons. We looked at data from elements 1 to 20 and reasoned from the energy needed to remove each electron that there must be levels within the atom with groups of electrons at about the same energy. We started with data that looked like this. Remember the groups of electrons at the different energies. This is the log plot. And we developed a model that looked like this. The shells of electrons at different distances from the nucleus represented groups of electrons at different energies that we saw in the data. So what we know about electrons. We know it takes energy to move things farther apart when they're attracted together, like an electron and a nucleus. So the farther out electrons are, the more potential energy they must have. Electrons closest to the nucleus have the lowest energies. We identified the outermost electrons in any atom as valence electrons, and we said they're really important because that's how atoms interact with other atoms, and that determines all of chemistry. And we saw how the number of valence electrons are related to position in the periodic table: 1, 2, 3, 4, 5, 6, 7, 8. Helium is an exception with 2. Transition metals are complicated. As we go across the table from left to right, the number of valence electrons increases from 1 to 8. And as we go down the periodic table, we add another electron shell for each row. And you can draw Bohr diagrams for bigger atoms, and they have more shells as you go further down. So we also looked at Bohr's model of the hydrogen atom. Now, hydrogen is significant because it only has one electron. So instead of layers of electrons at different energies, we have one electron, but we think that it can go further and further out to different orbits and change its energy. So we saw the one electron in hydrogen can absorb energy and jump to a higher energy state. Bohr drew these energy levels as orbits. It looks a lot like the shells we identified in many electron atoms are there, empty, able to be occupied by hydrogen's one electron if it could absorb the right amount of energy to get to them. All right, our first learning target says, know that the energy levels for electrons in atoms identified by N are called principal energy levels and correspond to rows of elements on the periodic table. The Bohr hydrogen atom has its energy levels labeled N equals 1, N equals 2, N equals 3, etc. We're now going to identify the electron shells in atoms as N equals 1, N equals 2, and so on. Whatever row an atom is in on the periodic table, that's the N level its valence electrons are in. N equals 1, first row. N equals 2, we got 2 levels, second row. N equals 3, 3 levels, third row. N equals 4, 4 levels, fourth row. So row 1, row 2, row 3, row 4. After calcium, it gets more complicated. All right, updating to the current model. It was a guess that electrons move in circular orbits. That model gave the right energies for hydrogen, but it turned out not to be right for any atoms with more than one electron. So what do we think now? Knowing that an electron acts like a wave, we turn to physics to tell us what a wave looks like when the wave has a negative charge and is attracted to a positive nucleus. Physics predicted a series of shapes. They are like standing waves. Well, they're funny looking. We call them orbitals because they replace the idea of orbits. So they're not orbits, but they replace the idea, so they're orbitals. We often say an electron is in a particular orbital. Rather than the little particle being somewhere in an orbital-shaped box, we think of the electron wave as taking the shape of that orbital. The electron is, smeared out over the whole region. Some people describe the smeared out electrons around an atom as an electron cloud. All right, our second learning target is know that the current model for electrons in atoms replacing Bohr's orbits is orbitals, which are regions of space around the nucleus having distinctive shapes. Our third learning target is to know the shapes of the s and p orbitals, the two simplest kinds. The simplest orbital shape is the s orbital. Although S doesn't stand for spherical, that may help you remember. There is one possible s orbital in each principal energy level. The s orbital in level n equals 1 is called the 1s. The s orbital in level n equals 2 is called the 2s. The s orbital in level n equals 3 is called the 3s, etc. The next simplest orbital is the p orbital. It looks like a dumbbell. There are 3 possible p orbitals in all principal energy levels except the first one. And they are identical in shape, but they have different orientations. One is in the x direction, one is in the y direction, one is in the z direction. So they're oriented at right angles to each other in x, y, and z directions. There are also d and f orbitals, which have more complicated shapes. Our fourth learning target is know how many of each type of orbital, S, P, D, and F, are in one sublevel. A group of orbitals of the same shape, S, P, D, or F, make up a sublevel. They come in groups, except for the S. It is a sublevel because the group is within a principal energy level, or n value. So you have your principal energy level, and then within that, you have sublevels that are S, P, D, and F. So we've already said there is one single s orbital in each principal energy level. There are 3 p orbitals in each energy level from n equals 2 on up. What about d and f? D orbitals come in sets of 5. There are 5 d orbitals in each level starting at n equals 3 on up. And f orbitals come in sets of 7. Starting at n equals 4, there are 7 f orbitals in each principal energy level. Think of orbitals as slots that electrons can go in. Each orbital can fit 2 electrons. The rules require 2 electrons in the same orbital to have opposite spins. We call them spin up and spin down. We represent them with arrows. Spin up electron is an up arrow. Spin down electron is a down arrow. So our fifth learning target is know how to assign electrons to orbitals to represent the ground state of an atom. We are representing atoms in the ground state. That means every electron is at the lowest energy available to it. To correctly represent the ground state, we're going to start at the lowest energy level and work up without skipping any levels. We will need a diagram showing energies of the orbitals. It looks like this. So we're going to start at the bottom. We're going to put electrons in the orbitals. We're going to build up the electron configuration for a particular atom by assigning electrons to orbitals starting at the lowest energy. Each orbital can hold 1 spin up and 1 spin down. So suppose our element is neon with 10 electrons. We want to place 10 electrons. We're going to start at the lowest possible energy, put 1 in the 1s. 2 can fit in as long as the spins are in opposite directions. So now that's full. It can only hold 2. So we're going to always go to what's lowest in energy. 2s is the lowest available. Put a spin up and a spin down. All right, now that's full with 2. Now, look at this. These 3 are at the same energy. So there's a new rule. We put 1 in, and the next arrow, if we have more than one orbital at the same energy, and that always means they're within a sublevel, they're P or they're D, then it's going to go in another orbital, and its spin is going to be in the same direction. And guess where the next one is going to go? We have a third orbital at the same energy, so 1's going to go in there with a spin in the same direction. And this is called Hund's rule, nicknamed the bus rule, because it says the electrons are like people in a bus. If there's an empty seat, they are not going to sit 2 to a seat. Once there's 1 electron in each of those orbitals, the 3s is much higher up, so the next electron is going to pair up with one of these, and the next one is going to pair up with another one, and the last one is going to pair up with the other one. And we have now placed 10 electrons, so this is what the orbital energy level diagram looks like for neon. Our last learning target is represent the electron arrangement in an atom using abbreviated orbital diagrams and electron configurations. So these are a couple of skills, and we're going to use some online sources and tools to develop them. All right, exit this. And we're going to go over to the first online source, and this is linked on the Canvas page. We're going to start in the middle. It starts talking about the periodic table. This link is to a pretty cool periodic table. Actually, let me show it to you. I already opened it. It has this nifty orbital energy level diagram at the bottom, and if you hover over any element, it will fill in all the appropriate arrows there. So you can build up hydrogen, helium, increasing numbers of electrons. And you can see, just like I said, they go in one at a time in these orbitals at the same energy. So back to here, we're going to start in the middle. The table has elements organized into columns and rows. The 7 horizontal rows correspond to the energy levels found outside an atom's nucleus. That's what we're talking about. The row any element is located in tells you what the highest energy level is that will be accepting electrons. For example, calcium, da-da-da-da-da. Okay, so then we go on to the next level, and it talks about the energy levels that I already went over. Then it goes into orbitals in a lot more depth. It tells you some kind of cool stuff about orbitals. Here's an s orbital. There's some diagrams of p orbitals in the different directions. It talks about filling orbitals, talks about d orbitals. Then it tells you about these 2 notations. This one is called writing an electron configuration. This is an abbreviated orbital diagram. And then it goes on to the cool interactive. Sorry, that was my cat. All right, so they give you an element. They tell you the atomic number. We're looking at electrons, but of course the number of electrons is the same as the atomic number. So they're going to have you drag objects here. We have a number of different orbitals down at the bottom. You will know more about these after you do the reading, and we can add electrons to the orbital. So if you start with a 2p, it doesn't think that that's the ground state. Let's go to the 1s. 1s is the lowest one. Yes, it will accept that. And then we put electrons in. And notice how they appear in the energy level diagram. So there you have helium. You can say done, and it will invite you to do another one. So that is the first thing. And then the second link that I have is another opportunity to build up some electron energy level diagrams. And this has all the elements up to number 18. Choose an element. Oh, sodium is very close to, well, we can do sodium. And this has a funny routine with clicks. The first click will give you 1 arrow. The second click gives you the down arrow. And if you want both, you kind of have to click 3 times. And if you click a 4th time, it can reset. So if you make a mistake. So sodium has 11 electrons. 2 are going to go on the 1s. That leaves 9. 2 are going to go on the 2s. That leaves 7. 2p, 1, 2, 3, 4. Have to click twice for each of these. 5, 6. So that's a total of 10. I've got 1 more, and it's going to go there. That should be correct for sodium, and there's a check answer box. It says correct. So try a few different elements and practice building these things up. Then I showed you that other table. There's also another cool table that I'm going to give you a link. P table. Once again, you can highlight an element and the orbital energy level diagram will be filled in. This also tells you up here the little electron configurations in case you need to check your work on writing those.